So my most favorite lesson dealing with chemical equilibrium is Le Chatelier's principle. Some of you learned about this last year, and hopefully you remember. Do you remember? Oh no, we're in oblivion. Well, that's because I know I can throw it out there, but then I got to turn my neck and it kills me, so I don't. All right. And if you didn't learn about it last year, it's really, really, really simple. Now, if when I go through you feel like you're missing a step, my honors lesson is on the YouTube channel if you need it. I don't think you will because you're super smart, but if you feel like you need a little backup, that's fine. All right. We're going to talk about qualitative type analysis of chemical equilibrium. So not numbers, not quantities, but qualitative. And this is what your lab's going to deal with next week. Very cool inquiry-based lab that we first put into place last year, and this year it should be better. So Le Chatelier's principle. This says when a change, and you can have a change in concentration, temperature, pressure, or volume, is imposed on a system that is at equilibrium, the system will respond in such a way to attain a new equilibrium that's going to minimize whatever it is that you changed. So for example, if you increase the concentration of reactants, equilibrium is going to shift in the forward direction in an effort to use some of those reactant or reactants up. That's what it is. All right. So, it's not going to get difficult. It's easy. All right. So, let's keep it very simple initially. In AP, I don't usually do A's, B's, C's, and D's. I'm going to march through, and if you need A, B, C's, and D's, we'll go back through them. Well, you'll see. You don't remember everything. All right. The first factor we're going to look at is concentration. It says if the concentration of reactant is increased, equilibrium will shift to the right or in the forward direction. Now don't say shift right, shift left. Equilibrium shifts to the right or in the forward direction. Before I go through all the wording, I'm going to rewrite this equation here and walk you through. So we have 4 moles of ammonia. Okay. 4 moles of ammonia in the gaseous state, 5 moles of oxygen gas, equilibrium conditions, generating 4 moles of nitrogen monoxide, and 6 moles of water vapor. And it does say here that delta H is negative 6.2 kilojoules. So is that endo or exo? Exo, and we'll come back to where that's relevant in a bit, not in this particular explanation. So A says if reactant concentration is increased, equilibrium will shift to the right or the forward direction. One thing I do want you to know or recall, when you increase the concentration or the temperature, equilibrium will shift away from that substance. Temperature, of course, is not a substance, but you'll see why I use that term. When you decrease concentration or temperature, equilibrium will shift. Now, I used back last year and the kids were confused. I'm going to get rid of the back. I'm going to say equilibrium will shift toward that substance. Okay? Now, without going through the examples here, if you increase concentration of either reactant, equilibrium must shift away from that substance. So, for example, if you increase ammonia concentration, equilibrium shifts in the forward direction, because if the reaction shifts forward, reactants will get consumed and products will get made. And Le Chatelier's principle says that when you impose some type of change on an equilibrium system, the system will react in such a way to at least partially undo the change you've made. So if you increase ammonia, equilibrium shifts in the forward direction to use some of the ammonia you added. So initially you increase this. When equilibrium shifts forward, it'll decrease. When it shifts forward, this will decrease. What will happen to the amounts of product? They will increase because they get generated. If you decrease oxygen concentration, when you decrease something, equilibrium must shift toward it in an effort to at least partially replenish what you have removed. So if you decrease oxygen, equilibrium will shift in the reverse direction to replace the oxygen that you removed. If you increase water vapor, equilibrium will shift to the left in an effort to use some of the water vapor you added. In shifting in the leftward direction, what happens to the amount of nitrogen monoxide? It decreases because it gets used, and these substances will increase in amount.
So at equilibrium, are there 4 moles of ammonia, 5 moles of oxygen, 4 moles of nitrogen monoxide, and 6 moles of water vapor?
In that ratio.
Yeah.
It's not to say you don't have 36 moles of this, but the ratio is there.
For that ratio.
But those are not numbers you'd plug in. Okay. All right. So I hit A and B. C says changes in solids or liquids don't affect equilibrium because they're not included in KC expressions. So if they break up a solid or they add more solid, there is no effect or no change on equilibrium. Be careful there. They always throw in a solid, and the kids are always like, woohoo, let's shift away from it. No, 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 no. These shifts are for gases and aqueous substances only. Let's take a look. It says, predict the direction in which equilibrium will shift when. If we decrease ammonia, so when I do this problem, I like to put a downward arrow right here. Well, that didn't work. Well, that's just a mess, but I guess you get the point. So if you decrease ammonia, equilibrium will shift to the
left in the reverse direction to replace.
Here's your equation. When you decrease ammonia, when you decrease, do you shift away or toward? Toward. So equilibrium shifts to the left or reverse direction to replace removed ammonia. Now it doesn't replace all of it, okay? So understand that with a leftward shift, if you are considering amounts of these substances here, you initially decrease this. With the leftward shift, it will increase. the oxygen will increase, and what will these two do? They will decrease. Whatever you point toward gets made, they go up, and the others go down for concentration. All right. The second problem says, if oxygen gas is decreased, equilibrium shifts to replace removed O2. And in doing so, you initially decrease this. So Le Chatelier's principle says, with the reverse shift, these substances get made and these substances get used. And the last one says, if NO increases, equilibrium, I'm not going to write in yellow, you won't be able to see it. Equilibrium shifts also to the left to use, not use all of it though, use the NO added, or you can keep your grammar the same. Sorry, Miss Detman, I apologize. All right? When you shift to the left, you initially increase this, and then what happens to the product amounts? They're going to decrease, and these will increase. All right? Let's take a look at another one. I'll have you try it. I just want to show you one thing. You could write KEQ expressions for this. If you wrote a KEQ expression for the next problem in your notes, which substance would you not include?
Water.
The water, because it's a liquid. All right? So water shouldn't alter equilibrium. Interestingly, here it does, because you've got a complex ion. Some of you may or may not remember, this is the reverse reaction that you ran in the lab last year. All right.
Can water be aqueous ever?
Water vapor, we live in Florida. It does wonders for my hair.
It's aqueous?
It's so humid down here, right?
But
Yeah.
it's aqueous.
It's steam. Oh, no. Well, you said aqueous. I'm sorry. I thought you meant gas. Oh, my joke wasn't funny then. Can water be in the aqueous state?
Can water
No.
be dissolved in water?
No. Water, you don't do aqueous. No. I'm sorry. I guess I didn't listen to the whole question. Joke's on my curls. All right. So here's your equation. You want to do it together or you want to try it? Let's do it together. Okay. It says, and these are complex ions. I'm not going to go over the naming here. One of your labs will have some complex ions in it. The naming is very, very interesting. Used to be assessed on the AP exam. Thank God it's gone. All right. So if this substance is decreased, equilibrium will shift to the reverse direction to replace this particular substance that was removed. All right. If chloride ion is decreased, equilibrium shifts in the forward direction to replace the chloride ion removed. Yes? Austin, yes? Jason, yes? Bailey, yes? Allie, yes? Mariana? Huh?
It doesn't replace all of it.
Correct. Now this is tricky. This is tricky. If you had hydrochloric acid, hydrochloric acid is a strong acid, right? It ionizes to H plus and Cl minus. So by adding hydrochloric acid, you're effectively increasing the concentration of what? Chloride ion. So if you increase the concentration of chloride ion right here, equilibrium shifts in the reverse or left direction to use the chloride ion added. Okay, this is super tricky. super tricky.
Is that not solid?
Super tricky.
Is it solid or is
Maybe
it
it's partially
so
solid.
this is not nice,
If you have this,
It looks like fine sheet.
right? See, I see.
really?
So that's C big O.
I know.
All right, so here's my equation.
It's exothermic.
It is exothermic, which is going to come into play in just a minute. In fact, we'll use this one to introduce in the next piece.
Okay.
Well, actually, for some reason in your notes, I did pressure and volume before temperature, which surprises me. I don't know why I would have done that. Whatever. All right. If you have silver nitrate, why is silver nitrate water soluble?
Nitrate.
Because all nitrates are water soluble. All right. So you effectively add that, right? All right. Now, all nitrates are soluble, so nitrate's not going to have an impact here at all. But what would the silver ion react with? Chloride?
Chloride ion.
So you'd have silver ion plus chloride ion making silver chloride a white precipitate that is not water soluble. So by adding silver nitrate, you are effectively decreasing the concentration of chloride ion because it's reacting with the silver ion. When you decrease chloride ion concentration, equilibrium shifts to the right to replace the chloride ion removed from reacting with the silver ion.
How do you know that it reacted with the chloride?
They would tell you you have a white precipitate.
Oh.
They'd have to tell you because you don't need to know that aspect of solubility rules. But silver chloride is a white precipitate, and I think I'd bury it in my brain somewhere because sometimes it pops up. Very often they give you this precipitation reaction, or if they want to be a little trickier, they'll give you lead-2 ion plus iodide ion, which makes lead-2 iodide, and that's a yellow precipitate. What?
PVI.
Exactly. Right. All right. The other thing I will mention before getting to it, just because it fits right here, and Austin pointed out that this reaction is in fact exothermic. If we increase the temperature, we're going to feed that into the heat term. If we increase the temperature, equilibrium will shift to the left to use the heat added. Now, with the concentration, when we altered one, something went up and down or down and up. But with heat, as we increase the temperature, equilibrium will shift to the left. These amounts will increase. These amounts will decrease. If I decrease the temperature, equilibrium will shift in the forward direction to replace the heat lost. These substances will have decreasing amounts. These substances will have increasing amounts because they'll get generated. Whichever direction the arrow points in signifies which substance will increase in amount. Yes, yes? We'll hit temperature in a bit. I don't know why I did volume next, but I did. What's the relationship between pressure and volume without looking at the screen? P over V. So as pressure increases, the volume decreases. No, it's PV.
Yeah.
P times V equals a constant. Oh, all right. Well, I feel better after the aqueous water humido. All right. So pressure and volume are inversely related. As one goes up, one goes down. Think about your bubble wrap. You're pushing down on that bubble. The volume's getting smaller and smaller until the pressure gets so great and it pops. And if you're babysitting, always fun to do with the kids, but put the bubble wrap away because they'll eat anything. All right. Changing the external pressure or volume. Let's take a look at the effect of volume or pressure on equilibrium. Now, I always do it from a pressure standpoint because it's easier for me, but whatever rocks your world is fine. All right. It says when the external pressure is increased or the system volume is reduced, equilibrium shifts in the direction producing the smaller volume of gases, which is determined by the stoichiometric coefficients of gases only. So if you increase the pressure, equilibrium shifts in the direction that has the smaller volume of gas, as determined by the coefficients. We'll do several examples. When you decrease pressure, equilibrium shifts in the direction that has the larger volume of gases. So again, you might even look at delta N of the gas. If there is no change in the volume, so if you increase or decrease pressure and the delta N of the gas is 0, there's no effect on chemical equilibrium. In yellow is AP level material, not something you would have seen in honors. It says if an inert or noble gas like helium, argon, etc., that won't react with your substances in there, which the noble gases don't typically do, although you do know you can generate xenon difluoride, xenon tetrafluoride. I don't think it'll get that complicated. If you add a noble gas at constant pressure, equilibrium will shift to the side with the larger volume so that you can accommodate this added gas. If you are a family of 4 and you come home from school and mommy's like, guess what, you're going to have a baby brother or sister, you need a bigger house. Same thing here. So if you add an inert gas at constant pressure, then you're going to, equilibrium will shift in the direction that has the larger volume of gas. However, if that gas is added at constant volume, there is no effect on equilibrium because you cannot change the volume regardless of the direction in which you shift. More commonly than not, you would see number 4, not number 5. Let's see if we can put all of this together as well as temperature. It says, consider the reaction generating nitrogen dioxide from nitrogen monoxide and oxygen gas. In which direction will a net reaction occur if additional nitrogen dioxide gas is added? Equilibrium will shift to the left to use the nitrogen dioxide added. In which direction will a net reaction occur if the reaction mixture is transferred from a 1.50 liter flask to a 3.50? So here's a situation where you're increasing volume. So you're going to shift to the side with the larger volume. So if you increase volume, you decrease pressure, right? Yeah. So you're going to shift to the side with the larger volume, so you're going to shift in the reverse direction because the volume of gaseous reactant, which is 3 mils, is greater than the volume of gaseous product, which would be 2 mils. So if you increase the volume, equilibrium shifts to the side of the reaction with the larger volume. This would be 2 plus 1 would be 3 mils or 3 liters, whatever volume unit you want, as compared to 2 mils or 2 liters.
Because you have more room to create the gas.
More room. In which, yeah. In which direction will equilibrium shift if the pressure is increased, equilibrium shifts to the forward direction because the volume of gaseous product, which is 2 mils, some of this you probably want to write out. Are you getting it down?
Yeah.
Okay. So the volume of gaseous product, which is 2 mils, is less than the volume of gaseous reactant, which is 3 mils, and we know pressure and volume are inversely related according to Boyle's law. And then the last piece is really the AP piece. It says, in which direction will equilibrium shift if neon were added at constant external pressure?
To the left.
It would shift to the left because the volume of gaseous reactants, which is 3 mils, is greater than the volume of gaseous product, which is 2 mils. The reactant side has a greater volume to accommodate the neon added. All right. And then the last two pieces of the puzzle are right here. We already hit upon the temperature aspect of it. I've always hated the explanations found in books. I think if you work temperature like a substance, life is easier. First of all, changing equilibrium temperature. The only variable that ever alters the value of Kc, or truly Kp as well, is temperature. No other factor alters the value of the equilibrium constant, only affecting the shift in equilibrium. When you increase temperature, equilibrium shifts in the direction of the endothermic reaction. When you decrease it, it shifts in the direction of the exothermic reaction. It says in most cases, solution formation's endothermic, which is why increasing temperature is going to facilitate substances dissolving in liquids, making them aqueous. The following reaction is given, and I gave you an exothermic reaction. I probably would not have put in what's in red. You would immediately put the energy term on the right side because it's exothermic. If you do that, you'll be more successful with your predictions. It says, in which direction will a net reaction occur if the temperature is decreased? If you decrease temperature, equilibrium shifts in the forward direction to replace the heat lost. Now the effect we've got to hit, because that's not something you may see. Well, I think you will see it as soon as I show it to you. All right, so we said if the temperature is decreased, equilibrium shifts in the forward direction to replace the heat lost, correct? Now, we know that Kc is that, right? Kc expression? Okay. So we shifted forward, correct? What happens to the amount of product? What happens to the amount of reactants? What happens to the value of Kc? Does that make sense? Whenever you shift forward due to temperature alterations, Kc will increase because the amount of product has increased, the amount of reactant has decreased. Whenever you shift in the reverse direction, you'll generate more reactant, you'll take away product, so the Kc value will decrease. So forward results in a Kc increase, reverse results in a Kc decrease. The next question says, in which direction will a net reaction occur if the pressure is increased? If I increase pressure, equilibrium will? You want to shift to the side with the smaller volume, so equilibrium shifts in the forward direction because the volume of gaseous reactant, which is 2 mils, is less than the volume of gaseous product, which is 3 mils, and we know, what did I do? Oh my God. Did I mess up the whole thing? If we increase pressure, equilibrium shifts forward. Oh, I just messed up that piece. That's because I'm a dummy. Did I say it right?
No.
So I totally messed it up? Oh, well. Staying up too late watching the Australian Open. All right. So the volume of gaseous product which is 2 mils, is less than the volume of gaseous reactant, which is 3 mils, in accordance with Boyle's law. Does that make sense since I made such a yucky mess? Okay. Now, this too is how questions come around, and sometimes you're like, oh, we didn't word it that way. What should I do? All right, it says, is the conversion of sulfur dioxide to sulfur trioxide more nearly complete at high or low temperatures? If we want the conversion, and just to be a total space, oh, well, there's a 2 there. Just, that looked funny to me. Okay. So if we're converting from SO2, sulfur dioxide, to sulfur trioxide, we're going in what direction? Forward.
So you want temperature to decrease.
So what's going to push this forward shift? Low temperature or high temperature? Low. Low. If you decrease temperature, equilibrium shifts in the forward direction, favoring the formation of sulfur trioxide. So it's more nearly complete at low temperatures because it is an exothermic reaction. Okay? So really make sure you're comfortable with that type of interpretation. There must be a very fun problem to do, which we will hit in a minute. In regard to adding a catalyst we know speeds up reaction rate by providing an alternative pathway that has a lower activation energy. However, it does not affect equilibrium, because if you increase the rate of the forward reaction, you're going to increase the rate of the reverse reaction. They're at equilibrium. So be careful here. A catalyst does not affect equilibrium. It affects the kinetic aspect, not chemical equilibrium. And that's something they might ask. These learning objectives we are going to hit big time in our lab. This illustrative concept is very, 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 very different than anything you've ever done, which is why we're going to reserve 50 minutes on Friday just to hit this and to address anything you may have. We have a good 10 minutes. This is a problem in an old textbook that I'm going to pull out. We can work together. I wouldn't touch the Poggle packet yet. I think that's a perfect thing to work on Friday when we've gone through our lesson. I will say this. Before Friday, you should have homework done through Le Chatelier's principle. The more you do, the better you're going to be at it. The AP exam has gotten very qualitative. Somebody left what looks like a very nice watch on my desk.
Looks like it's broken. I think
It is broken and it's mine.
In any event, that homework through Le Chatelier's principle should be done for next time if you really want to understand equilibrium. If you can make a significant dent before Friday, you really can work on learning this material in little chunks for next Friday. I think you'll be a lot more successful with that. There are 3 AP Insight quizzes here. I'm going to go through them carefully. I'm going to give you the one or ones that are most helpful for you. If you didn't do it last time, you made a mistake, you saw an identical question on the quiz, I didn't even change anything to it. And if you missed it, I know you didn't do the AP Insight questions. So what? You made a mistake. You are super, super smart, the smartest kids in the whole school. Don't make the same mistake twice, okay? When I unlock it, I'll let you know. I want to look through it and see which questions are best for you so they won't be overwhelming. You had a question.
If it's endothermic, is the heat going to be on the left side of the screen?
Yes. All right. This other question I'd like to take a look at. This is in an old textbook. But I must think it's a good one if I left it here. What page? Oh my gosh, 1616. That's like not even a page number. Oh look, I opened right to it.
No, you didn't.
Yeah, I really did.
Oh, you have milk things.
No, I don't have a thingy in there. It just opened. Oh, I do have one right here, but I didn't use it. All right. Here we go. We'll do it together. But if I give you a little quiz on this next time, I expect 100. No pressure, though. Here we go. First of all, Austin, endo or exothermic reaction?
Endo.
So energy's going?
On the left.
Good. In which direction will this equilibrium be shifted by the following changes? If I add dinitrogen monoxide, equilibrium shifts to the right is correct. If I remove nitrogen dioxide, sorry, it shifts to the left. If I add nitrogen monoxide, it shifts to the left. If I increase temperature, the energy's right here, so it shifts to the right. Now, if I add helium at constant volume, there is no effect. If I decrease the volume of the container at constant temperature, I shift to the side with the smaller volume, so I shift to the left. You feeling good about Le Chatelier's principle?
Yeah.
Especially those of you who are new to it. All right. If you want to go back and watch the honors video, it is on the YouTube channel. It goes in baby steps to explain the concept. You guys are super bright. I don't think you really need it, but if you feel like you want it, you've got it. Some Le Chatelier principle questions are good, and that's what I started to say, is that what I'm seeing more and more of is the AP exams getting very conceptual. So you might see a part 2 question dealing with Le Chatelier's principle. You pray for those. Now, even if you see it with a graph, you don't freak out. It's very manageable, and you should do extremely well on that type of question, and we're going to do the lab next week. All right, we will do illustrative equilibrium next time. It's very calculation-based. If you have a graphing calculator, bring it. It'll come in handy. For those of you who are going to be out, I will record.
Thank you.
All right, so hopefully a more solid understanding of chemical equilibrium.